Good morning, students. In the previous session, we have seen types of electrochemical cells, that is electrolytic cell and galvanic cell or voltaic cell. Electrolytic cell is nothing but the cell which converts electrical energy to chemical energy. That means by consuming electricity, chemical reactions takes place here. But in galvanic cell or Daniel cell or voltaic cell, chemical energy converts to electrical energy. Yes, that means due to the chemical reactions, that is redox reactions, electricity is producing in galvanic cell or Daniel cell. So now let us say, now let us start today's session. That is Nernst equation, expression of Nernst equation. Nernst equation at room temperature, that is at 25 degrees centigrade. Derivation of Nernst equation, determining equilibrium constant at equilibrium conditions, and applications of Nernst equation. So let us see what is Nernst equation. Maybe in the intermediate level you have seen only the Nernst equation, but now let us see the derivation and applications of Nernst equation. The Nernst equation provides a relation between the cell potential of an electrochemical cell, the standard cell potential, temperature, and reaction quotient. Yes, so here the Nernst equation is nothing but it is the relationship between the cell potential. So what is the cell potential? Potential of the cell, that is EMF, E cell of an electrochemical cell, the standard cell potential, that is E naught cell, temperature, and reaction quotient. Yes, so here the Nernst equation is giving the relationship between E cell, E naught cell, temperature, and the reaction quotient. Even under non-standard conditions, the cell potential of electrochemical cell can be determined with the help of the Nernst equation. Previously, we have calculated only the cell potential at the standard conditions. What are the standard conditions? Room temperature, 1 molar concentration of an electrolyte, and 1 atmospheric pressure. Yes, so these are the standard conditions. At this standard condition, we have calculated the cell potential. That cell potential is called E naught cell. That is a standard cell potential. But by using Nernst equation, we can find the cell potential even at the non-standard conditions. That means at any temperature, at any pressure, at any concentration, we can find the Nernst equation, we can find the cell potential by using Nernst equation. So the Nernst equation is often used to calculate the cell potential of an electrochemical cell at any given temperature, pressure, and the reactant concentration. The equation was introduced by the German chemist. So his name is Hermann Nernst. So that's what I told now. The Nernst equation is often used to calculate the cell potential. That means E cell at any temperature, pressure, and the concentration. Yes. So this is about the Nernst equation. So now let us see the expression of the Nernst equation. So how to write the Nernst equation? What is the Nernst equation? Nernst equation is an equation in which reduction potential measured at any conditions to that measured at standard conditions of 298 Kelvin and 1 molar or 1 atmospheric pressure. So in this, it is relates. That means it is having the relationship between the reduction potential measured at any conditions. That means E and E naught. E cell and E naught cell, or E and E relation is nothing but the Nernst equation. So let us see the expression of the Nernst equation. This is the expression of the Nernst equation for the not single electrode potential. This is for the cell potential. This is for the cell potential. So here E cell is equals to E naught cell minus RT by NF ln Q. This is the Nernst equation, and in this Nernst equation we are calculating the cell potential. E cell is equals to E naught cell minus RT by NF ln Q. Yes, so this is a cell potential, that is EMF. E naught cell, that is a cell potential at the standard conditions. R is a universal gas constant, and T is the absolute temperature, and N is number of electrons transferred in the redox reaction. That means either loss of electrons or gain of electrons. So number of electrons lost or gained, that is N. F is the Faraday constant, and Q is the reaction quotient. So I'll explain you about reaction quotient in the next slide. Yes. So that is the Nernst equation. So simply remember E cell is equals to E naught cell minus RT by NF ln Q. So now the calculation of single electrode reduction potential. So previously we have seen the cell potential, that is the potential of the entire cell. But now we are seeing the reduction potential, that is a single electrode potential. Single electrode means either for anode or for cathode. So the same expression is also applicable with a single electrode. So there we have written E cell. So instead of E cell, we can write E red. E red is nothing but reduction potential of electrode. Yes. So the calculation of single electrode reduction potential, that is E red, from the standard single electrode reduction potential E naught red for an atom or ion is given by the Nernst equation. So here it is giving the relation between E red and the E naught red. So for a reduction reaction, so we can take redox reactions. That means we can take either reduction reaction or the oxidation reaction. That means we can apply the Nernst equation either to the anode or to the cathode. Because reduction means the electrode is acting as a cathode. Oxidation means the electrode is acting as the anode. So this expression is applicable for both redox reactions. So now we are taking the example reduction reaction. For a reduction reaction, Nernst equation for a single electrode reduction potential for a reduction reaction is Mn plus n electrons giving rise to Nm. Yes. So this is the reduction reaction. So what is reduction reaction? Gaining of electrons. Gaining of electrons is called reduction reaction. So we are taking the example of metal Mn plus n electron giving rise to Nm. Yes. So this is the reduction reaction. Here the metal is having the n number of electrons deficiency. So it is gaining n number of electrons. That means it is adding the n number of electrons to produce a neutral atom, that is Nm. So let us apply the Nernst equation to this particular reaction. E red, here red is nothing but reduction. So what is the reduction here? Mn plus is converts to M. So that's what we have written here. E Mn plus M. It means Mn plus is converts to M. E Mn plus M is equals to E naught Mn plus M minus 2.303 RT by NF log 1 by Mn plus. Yes. So here E is equals to, in the place of E cell, what we have written? E, the reduction reaction, is equals to E naught reduction minus 2.303 RT by NF log 1 by Mn plus. So here 1 by Mn plus is nothing but Q. So see here we have seen Q here. Yes. So there is a lot of difference between that reaction and this reaction. Yes, this expression. Here E cell, in the place of E cell, what we have written? E Mn plus M is equals to E naught Mn plus M minus, what we need to write there? RT by NF ln Q. RT by NF ln Q. I said this is Q. So what is extra here? 2.303 log is extra. That means we can write in the place of ln 2.303 log. Yes. So this is the same expression, but here it is applicable to single electrode potential also. So where R is the universal gas constant, The value of R is 8.314 joules per Kelvin per mole. And T is the absolute temperature in Kelvin. N is number of electrons. F is Faraday constant. That Faraday constant value is 96,487 coulombs. So approximately we can write 96,500 coulombs per mole. It means the charge carried by 1 mole of electrons. Mn plus. So here we are having Mn plus. Active mass of the ions. For simplicity, it may be taken as equal to the molar concentration of the salt. So here square brackets is nothing but the concentration. So concentration of the electrolyte. Yes, if the metal is having any charge, that is the electrolyte. So concentration of the electrolyte. So I'll explain you later why we have written in the place of Q 1 by Mn plus. So this is the Nernst equation for the single electrode. So now let us see the main topic, that is derivation of Nernst equation. So let us see how to derive the Nernst equation. Consider a metal contact with its own salt aqueous solution. Reactions of metal losing an electron to become an ion and the ion gaining an electron to return the atomic state are equally feasible and are in equilibrium state. So what we are saying here, consider a metal in contact with its own aqueous solution. So when the metal is contacting with its own salt solution, what happens? It develops the potential. Yes, that is the electrode potential. But here either the electrode is losing electrons or gaining electrons. If the metal losing an electron to become an ion, it is true. When the metal is losing electrons, what happens? The metal gets the charge. That means metal is converts to ion. But when the ion gains the electrons, we will get the neutral. But always the oxidation and reduction, these are feasible and these are in the equilibrium state. So in the reduction reaction, so now we have considered the reduction reaction here. You know what is meant by the reduction reaction? Gaining of electrons. So here Mn plus is gaining n number of electrons to produce Nm. So in the reduction reaction, n moles of an electron is taken up by the ion against a reduction potential of E red. Yes, so this ion is gaining the n number of electrons to produce the electrode potential, that is E red. But when it is gaining the electrons or losing the electrons, it will be doing some work. Yes, there is some work done. So the work done in the movement of electrons is W red is equals to NF E red. So this is from the thermodynamics. Work done is equals to NF E red. So you know what is E red? That is the reduction potential. And this is the work done for the reduction. So work done for the reduction is equals to NF E red. So where F is the Faraday constant. So already we have seen that. So you remember this from the thermodynamics. We got work done is equals to NF electrode potential. That is the reduction potential. But from the thermodynamics, we are having one more expression. That is change in the Gibbs free energy is an indication of the spontaneity. And it is also equal to the maximum useful work done in a process. So here, due to the transfer of electrons, there is a change in the Gibbs free energy. But here change in the Gibbs free energy is indicating there is a maximum of work done. Yes, but we know what is the maximum of work done here. But here the change in the Gibbs free energy is indication of spontaneity. That means it is a natural process. So for the spontaneous process, change in the Gibbs free energy is negative. But whereas for the non-spontaneous process, change in the Gibbs free energy is positive. But we know that change in the Gibbs free energy is negative. It is equals to the maximum of the work done. But from this expression, we know that W is equals to NFE. But what is the maximum of work done? It is the negative sign of the change in the Gibbs free energy. So negative sign is nothing but minus. Change in the Gibbs free energy is nothing but delta G. So that's what we are writing here. W red is nothing but NF E red from this. But we know change in the Gibbs free energy is equals to maximum of work done, and it is a spontaneous process. So W red is nothing but minus delta G. So minus delta G is equals to NFE. So we can write delta G is equals to minus NFE. So delta G is equals to minus NFE red. Yes. So this is the change in the Gibbs free energy is equals to minus NFE red. So you remember this. But now we need change in the Gibbs free energy at standard conditions also. Change in the Gibbs free energy at standard conditions. What are the standard conditions? Room temperature. What is the room temperature? 298 Kelvin or 25 degrees centigrade. If 25 degrees centigrade is converts to Kelvin, you will get 298. But how we got the degree centigrade to Kelvin? By adding 273. So if we add 273 to 25, we will get 298 K. That is 298 Kelvin. And 1 molar or 1 atmospheric pressure conditions is delta G naught. Yes. So we know that at standard conditions, electrode potential is E naught, cell potential is E naught cell, and change in the Gibbs free energy is delta G naught. So from the above relation, it can be written that, what is the above relation? This relation. So here delta G is equals to minus NFE. So we can write delta G naught is equals to minus NFE naught. Yes, because N naught we can't write because N is the constant. We can't write F naught because F also constant. But we can write E naught because E is not constant, it is the variable. So we can write delta G naught is equals to minus NF E naught. Delta G naught is equals to minus NF E naught. But where E naught red is nothing but, what is E naught? The standard conditions, electrode potential at standard condition. E naught red is the reduction potential measured at standard conditions. So what we need to remember here, delta G is equals to minus NFE, delta G naught is equals to minus NFE naught. And during the reaction, concentration keeps changing and the potential also will decrease with the rate of reaction. Yes. So when the reaction is progressing, what happens? The concentration of electrolyte is changing here. Due to that, the potential also changing. But it should not happen here. To get the maximum work or maximum free energy change, the concentrations have to be maintained the same. This is possible only by carrying out the reaction under a reversible equilibrium conditions. So when we are maintaining the equilibrium conditions, then the concentration will be same and there is no change in the potential value. So for a reversible equilibrium reaction, so when we are taking the reaction to the equilibrium conditions, want of isotherm says delta G is equals to delta G naught plus RT ln K. So at the equilibrium conditions, we can write K in the place of Q. Delta G is equals to delta G naught plus RT ln K. Yes. But from the above expression, we know what is delta G, what is delta G naught. And before that, let us see what is K. K is the equilibrium constant. K is nothing but products concentration divided by reactants concentration. But before that, you know what is product, what is reactant here. Product in our example. What is the example here? This is example. This is the product and this is the reactant. Product divided by reactant concentration. That is K here. Product divided by reactant. R is a gas constant. The value is 8.314 joules per Kelvin per mole. And T is the temperature in Kelvin scale. Yes. So now we got the change in the Gibbs free energy. that is the want of isotherm, that is delta G is equals to delta G naught plus RT LNK. But we know what is delta G, what is delta G naught. Delta G is equals to minus NFE. Delta G naught is equals to minus NFE naught. So let us substitute in the place of delta G minus NFE, in the place of delta G naught minus NFE naught. So when we substitute minus NFE naught in this expression, we will get minus NFE is equals to minus NFE naught plus RT ln K. But you know what is K? K is products concentration divided by reactants concentration. So here product is m power n divided by mn plus. Here if metal is not having any charge, that is a pure metal, that is solid. But when the metal is having any charge, that means if the metal is an ion, that is electrolyte. You know what is mean by electrolyte here? The metal that is a solid concentration always equals to 1. The liquid concentration is not equals to 1. Yes. So that means which concentration is equals to 1? This concentration is equals to 1 because it is a solid. So we can write before that, let us divide both sides with minus NF. When we are dividing both sides with minus NF, this minus NF gets cancelled. This minus NF gets cancelled. So what we will get here? See here, when we are dividing this with minus NF gets cancelled. So the remaining is E red is equals to E naught red plus 2.303 RT by minus NF log m power n divided by m power n plus. But here we are having divided with minus NF. That means plus into minus becomes minus. Minus 2.303 RT by NF log m power n divided by m power n plus. So finally what we got? E red is equals to E naught red minus 2.303 RT by NF log m power n divided by m power n. So this is the general Nernst equation. So when we apply, the metal concentration is equals to when we substitute in this, so we can write in the place of this one. So that is A red is equals to E naught red minus 2.303 RT by NF log 1 by m power n plus. So this is the derivation of Nernst equation. So this relation connecting reduction potential measured at conditions other than standard conditions to the standard electrode potential is the Nernst equation. So simply it is a relation between the electrode potential at the non-standard conditions and the electrode potential at the standard conditions. So now let us see the Nernst equation at 25 degrees centigrade. So directly let us see. For reaction conducted at room temperature. So what is the room temperature? 25 degrees centigrade. But I said you now how to convert centigrade to Kelvin by adding 273. So when we add 273 to 25, we will get 298 Kelvin. So for reaction conducted at 298 Kelvin, but at different concentration. That means the electrolyte concentration is different. Nernst equation is, so let us see what are the values at the room temperature. R is always universal gas constant 8.314 joules per Kelvin per mole. T is the absolute temperature, that is the room temperature 298 Kelvin. So here I have mentioned how to convert centigrade to Kelvin, 25 degrees centigrade plus 273. And F is the Faraday constant, that value is 96,487 coulombs. So now let us substitute these values in this formula. So what is the formula? This is the formula. So when we substitute all the values in this formula, these two R remains as it is. R is 8.314, T is 298 and F is 96,487. By substituting all the values, you will get the Nernst equation at room temperature. E red is equals to E naught red minus 0.059 by n log 1 by m power n plus. So in the place of this, you can write k log k. Yes. So either you can write 1 by mn plus, or you can write log k. Yes. So or else you can write this, or else you can write log k. Yes. So that is the Nernst equation at room temperature. So now let us see the reaction quotient or the equilibrium constant. Already I explained you there the product's concentration divided by reactant's concentration. But again, I'm giving this definition along with the examples. Reaction quotient, it is defined as the ratio of products and the reactants concentration. So reaction quotient or equilibrium constant, both are same. But equilibrium constant at equilibrium conditions, reaction quotient at the normal conditions. So Q or K is equals to products concentration divided by reactants concentration. He already told you that the concentration always must be mentioned in the square brackets. So products concentration divided by reactants concentration. So let us take one example. In this example, I have given only one reactant, only one product. Small a moles of capital A producing small b moles of capital B. So here small a is the number of moles, small b also number of moles. Before the arrow, those are the reactants, and after the arrow, those are the products. A is the reactant and B is the product. So let us see how to write K or Q. So Q is equals to products concentration divided by reactants concentration. So if we don't have A and B here, that means if we have one A and one B, that means if reactant and product number of moles are 1. So how to write B by A? But here we are having small a moles of A and small b moles of B. So we can write the quotient, reaction quotient as B power B. That means the number of moles must be on the power. B power B divided by A power A. Sorry, here capital A. A power E. Yes. So if I am giving this example, what you will do here? If I am giving this example, how you will write 2A giving rise to 3B. So how you will write here? Q is equals to B power 3 divided by A power 2. So always number of moles must be on the power. So in this case, I have taken only one reactant, only one product. So in this example, I have taken 2 reactants, 2 products. What are the reactants? Before arrow, reactants, after the arrow, products. So Q is equals to C power C into D power D divided by A power A into B power B. Yes. So that is the equilibrium constant or the reaction quotient. So in this session, what we have seen now, the derivation of Nernst equation at room temperature. So what is the Nernst equation? It is a relationship between electrode potential, standard electrode potential, temperature and the reaction quotient, or the relation between cell potential, standard cell potential, temperature and the reaction quotient. That is the Nernst equation. So we can write the Nernst equation as E cell is equals to E naught cell minus 2.303 RT by NF log K or Q. This is for the cell potential. And for the single electrode potential, E red is equals to E naught red minus 2.303 RT by NF log K. And here K or Q is nothing but products concentration divided by reactants concentration. Yes. So now let us see the determination of equilibrium constant with the Nernst equation. So we can find the equilibrium constant. So what is the symbol of equilibrium constant? Equilibrium constant symbol is K. So here we have seen the K value. So this is K, that is the equilibrium constant. So let us derive the equilibrium constant value by using Nernst equation. When the reactants and the products of the electrochemical cell reach equilibrium, that means the forward reaction and the backward reaction with same speed, that is the equilibrium. So when the reactants and products are reaching the equilibrium condition, the value of delta G becomes 0. At this point, the reaction quotient and the equilibrium constant are the same. Since delta G minus NFE, the cell potential at equilibrium also 0. So delta G value is equals to 0. Yes. So when this value is equals to 0, we can substitute this value in the formula. But what is the formula? E cell is equals to E naught cell minus RT by NF ln K. That was the formula. So what we are doing here, in the place of E cell, we are substituting, because if delta G is equals to 0, E cell also equals to 0. So when E cell is equals to 0, we can substitute 0 and E naught cell minus RT by NF ln K. So at equilibrium condition, E cell value is equals to 0. Now the relation between the Nernst equation, the equilibrium constant and Gibbs free energy change is illustrated below. So we can write here. So E naught cell is equals to RT by NF. The same thing I'm copying here. So when this value goes to the left side, what we will get? So here we will get equals. So we will get E naught cell is equals to RT by NF ln K. So this, by using this formula, or else what we can do, this value goes to the denominator. So we will get ln K, that is ln K is equals to E naught cell by RT by NF. Yes, so that means we can write NF E naught cell divided by RT is equals to ln K. Yes, so this is the formula to find the equilibrium constant value. So finally we will get ln K is equals to NF E naught cell divided by RT. Yes, so this is the derivation of equilibrium constant by using the Nernst equation. So let us see today's last topic, that is applications of Nernst equation. So what we can find by using the Nernst equation? Yes, so what are the applications or what are the uses of Nernst equation? The Nernst equation can be used to calculate single electrode reduction or oxidation potential at any condition. So already we have seen, yes. So E red is equals to E naught red minus 2.303 RT by NF log K. So by using Nernst equation, we can find single electrode reduction or oxidation potential. Standard electrode potentials, we can find even standard electrode potential values also at equilibrium conditions. Comparing relative ability as a reductive or oxidative agent, and finding the feasibility of the combination of such single electrodes to produce electric potential, EMF of an electrochemical cell, unknown ionic concentrations, that means we can find the concentration of this. We can find the concentration of this if we know E naught value, E value. Yes, if we know these two values, can't we find the concentration of the particular compound? Yes, we can find the concentration of the unknown solution. And the pH of solutions and solubility of sparingly soluble salt can be measured with the help of the Nernst equation. So even we can find the pH also, that I will explain in the numericals. So how to find the pH value by using the Nernst equation, and how to find the concentration of the given solution, that means unknown solution, and how to find the EMF, that I will explain in the numericals. Yes, so these are the applications of the Nernst equation. Yes, So thank you so much, Ma.